Sound is an important part of perception. When we view some sort of physical interaction, we expect to hear sound feedback. In this class, we have spent a great deal talking about how to simulate the physical world visually. So for the final project, we decided to look at audio simulation. The paper we're implementing for our simulation is Interactive Sound Synthesis for Large-Scale Environments. This paper explains a spring mass model to solving the problem of sound generation. Given an input geometry, we can describe the geometry as a mesh and translate the mesh into a mass spring system where each vertex of the mesh is a mass and each edge is a spring. When collision happens in the mass spring system, the system will oscillate with respect to the impulse force. Because sound is a result of physical vibrations that travel through a medium, we can attempt to derive the sound waves from the oscillations of this mass spring system. We first simulated this approach in MATLAB for the general case of an 8-vertex cube. For our calculations, the mass spring system is represented by two matrices, the mass matrix and the elastic force matrix. This is an image of the elastic force matrix, where the grayscale colors represent the magnitude of the force between two nodes. White is where the most force is, and black is where there are no force. This is the graph of the modes, or different signals from each individual spring generated by our program. The sample rate is 44 kHz. After we sum the different modes, we get this as the total audio signal. It sounds like. The time complexity for calculating sound at 44 kHz is big O of number of mode times sampling frequency for 1 second sound clip, or 24 times 44 kHz in this example. To speed things up, we tested at sampling frequencies as low as 8 kHz and clipped out parts inaudible to the human ear. This is the graph of sampling the cube at 8 kHz. And this is the resulting sound signal after summing all the modes. The sound is. For our final product, we use boom blocks as the base code, eigen for linear algebra calculations, and fmod for sound management. In this first result, we're shooting a sphere into the screen. As the sphere gets farther away from us, the sampling rate of the sound decreases. In the next few examples, we're dropping cubes of various constants to simulate different materials. In this example, we're dropping multiple objects at the same time. In this last example, we were able to import our sound generation code into Teacher Thomas's Angry Spheres game.
Given more time, future development for this project could include different geometry, an object loader, and using a more efficient collision detection system, and try to simulate rolling sounds.